Hi, everybody. My name is Marta Monelli, and I am a second-year PhD student working in HEO's group at MPA. And yes, today I would like to present to you what I've been working on in the past 6 months, more or less, which is an attempt to build up a simulation pipeline for a LiteBIRD-like experiment based on beamconv. So basically is what Alex just said, trying to apply all the machinery to satellite CMB experiment. If you have questions, whatever time, just raise your hand, so maybe we can just deal with them as they come. So the sketch of the pipeline is more or less this. The two main dependencies are beamconv and also duck. I'm using beamconv, which is, I'm not going to repeat what beamconv is because I think it's clear at this point, but I wanted to stress, as Jon was saying, that is, it has this very, very nice feature of being able to deal with polarized beams together with halfway plate non-idealities. And I'm using beamconv given all the important inputs to produce the time order data, while duck, which is this collection of a lot of programming tools developed by and cured by Martin Reinecke, I'm using just a very small functionality to produce a realization of the noise to add to the TOD to get a more realistic result. And also I am simulating the dipole modulation, and I'm doing so by basically using the same functionalities as they are in the LiteBIRD sim dipole module. So I'm just not using LiteBIRD sim. It was a way to just be independent from LiteBIRD sim, but I'm mimicking what they're doing basically. So I would like to go through all the inputs here that you can see to see how we specified beamconv to LiteBIRD case, and then we will get to a notebook and see how things are done in a little bit more detail. Okay, so the things that beamconv needs, as Alex was saying, are some input maps, some scanning strategy specifics. Then you need to define your focal plane with all the detectors, their positions, and their polarization angle sensitivity. And you can add the halfway plate. And in case you want to include non-idealities, you need to know what these non-idealities are. Another thing that I'm missing at this point, and we would say it a bit later, is, I see something on the chat.
Oh no, don't mind
okay.
that.
Is more realistic beams, which I'm not including yet. But yeah, with beamconv, it should be like a pretty straightforward thing to do. And about the, oh, why is not going? Okay, about the input maps, I'm just using PySM to simulate a map with CMB signal and foreground emission. And at this point, my pipeline is only able to deal with a single frequency. So I just took the band center of a frequency channel of LiteBIRD, and these are the maps for intensity, QNU, Stokes parameters that I get. In the future, I would like to extend it to deal with a lot of frequency and performance integration, but I'm not there yet. About the scanning strategy, this was a bit tricky because we decided to implement inside of beamconv. We had this satellite scan branch. We decided to implement in there the possibility to have a realistic scanning strategy for a satellite at L2, like LiteBIRD is. And in order to do so, we took some functionalities from PyScan, which is a code developed by Tomotake Matsumura that is being used in LiteBIRD sim, and put them into beamconv. So basically now, given the precession angle and the borosight angle and their periods of rotation, beamconv is able to produce pointing for the borosight direction at any point, at any time that you want. And what we get with beamconv now is this hits map. This is just for 5 days, but it looks a lot like how a hits map for LiteBIRD should look like. So we're pretty happy with how it turned out. And about the focal plane specifics, I'm reading everything from the IMO of LiteBIRD. So, and I hope that with the new version of the IMO, the code should still be able to just read from them, because I hopefully they're going to to leave the format as it is right now. And the IMO contains a lot of dictionaries basically for all the detectors and all other interesting objects for the mission. For instance, for a detector, you have these huge dictionaries. Here I'm missing a lot of entries because there were too much, like with name of the detector, the wafer of the detector, the pixel in the focal plane, and so on. And what was relevant for the most relevant thing for beamconv is this pole, orient, and quad quantities that specify the this is the quaternion associated to the fact that the detectors have an offset position on the focal plane. They are not at the bore site, and T and Q encodes how the polarization direction of the detector, which is the sensitivity, which is the direction on which the detector is sensitive to polarization. And yeah, and for the halfway plate, Gianpaolo Pisano gave us a file with all the John's matrix elements for the halfway plate, and we translated it into a Mueller matrix, which in the ideal case, the Mueller matrix for the halfway plate would be just this diagonal matrix. But when you take into account non-idealities, you have quite strong frequency dependence, and of course you get also off diagonal elements. So these are the Mueller matrix element, which are actually functions basically of the frequency that we get from what Gianpaolo gave us. Again, you see here the frequency dependence that it's important to account for, but right now I'm only dealing with one frequency. So I'm just looking at the band center frequency and taking these, just a number, as the Mueller matrix element.
Marta, can I interject just really quickly?
Sure.
Just the statement that we haven't checked with Gianpaolo whether or not, so these calculations that convert the results from Gianpaolo's optical simulations into this Mueller matrix, we haven't yet touched base with him to see if he agrees with these results. So take the Mueller matrix that you're looking at right there, take it with a grain of salt.
Yeah, sure. But I mean, right now, everything is very preliminary.
Yeah. I just want to know, so if people are looking at like QI or something like that and raising an eyebrow, don't put too much energy into it. Yeah.
Good point. And so, yeah, these are the inputs that I'm using for running beamconv, like the real beamconv part. And then there is the noise that is dealt by DAC. And DAC is able right now, given all these parameters for the noise power spectrum, to produce a realization of the noise. And these are again given in the IMO. So I just read these parameters from there and run DAC. Here I am showing the noise power spectrum. The red line is this formula as a function of the frequency, while this gray line is the power spectrum obtained by averaging 300 realizations of DAC. If you go with an higher number, it looks even more, of course, even more similar to the theoretical power spectrum. And then once I have the noise only TOD, I can just sum it up with this noiseless component. For the dipole, which is the last thing that I've been implementing, as I was saying, I'm following the same procedure as the one employed in the dipole module in LiteBIRD Sim, with just a few minor tweaks, but they're not really interesting at this point. And I get something like this. Okay, so I think, yeah, once you have all these three ingredients, you can just put them together. And here I'm showing the comparison of the noisy, so noiseless plus noise, and noiseless TOD. There is no dipole in this plot. But yeah, I mean, this is just the time order data for a single detector after a day of observation. And we see the noise is most visible here in the bottom, while on the top part, the signal is dominated by foreground. So the darker green is almost invisible. You can only see here a bit. And in case you are wondering what is this sort of periodicity in the signal, we checked, and it's actually corresponds to a precession period. So after, between these and these other orange vertical lines, the detector is looking at similar regions of the sky, almost the same region of the sky. So we obviously observe similar signal.
What's the orange color here?
It's just to, yeah, these are the time corresponding to precession periods. So
I
from
see.
one
Okay.
orange to the other, there is a precession period.
So it's not a signal or anything. It's just a...
No.
Okay.
Lady?
Sorry, was somebody saying something? No. Okay. And yeah, so we can maybe go on this notebook and go a little bit more in detail. Of course, I need to import all the relevant things and to produce the input maps. And as Alex was showing before, there is this object in beamconv that is scan strategy. And I'm initiating two of them, 1 and 2. The first one would be without alpha plate non-idealities, so only the ideal case. And this one instead includes non-idealities. At this point, they are identical. There is no difference, but we will see when we include the alpha plate that I'm going to pick a different Mueller matrix for the two of them. Also for the scanning strategy, except defining and initiating the object, we actually need to provide a QBOR func that is a function in beamconv. It's basically the function that beamconv uses to produce the Borsight quaternion at each time. And here I'm using this LiteBIRD scan, which implements all the functionality of PyScan. So all the information about PyScan is in this LiteBIRD scan function. And yeah, at this point, the two scanning options are still the same. There is no alpha plate yet. And I'm just dividing the mission in chunks, even if it isn't really relevant at this point. This is the code that we use to go from the Jones matrix element to the Mueller matrix element that I was showing you before. And here I'm just picking only one frequency. So I have this Mueller 140 gigahertz, which is this matrix you see here. This part of the code is used to read the focal plane specifics from the IMO, which then I will use to build up the focal plane as Alex was showing before. So for each detector, I have all this information on the IMO, the full width of maximum of the beam, the elasticity, the band center bandwidth, etc., plus this pole, orient, and quad quantity that tell me which is the offset position. They encode the offset position of the detector on the focal plane and the direction sensitive to the polarization. And I can finally create the focal plane with this input focal plane function that was also showed by Alex. Here, the interesting thing is that we implemented a way to read the offset quaternions directly from an external file, while before in beamconv they were produced given this AZ and L quantities. But right now, by specifying them in the beam options 1 and 2, I can just pass the offset quaternion to, and they are taken into account in the focal plane. And here, finally, there is some difference between the two scanning strategy objects, because in the first case, I'm setting the Mueller matrix to the diagonal case, the ideal case, while in the second case, I'm using the Mueller matrix that we calculated before. And yeah, and now we have a scanning strategy with the focal plane that we can use to produce the time ordered data. We do what Alex was doing before. So we allocate the maps, we do the scan, and we end up with this. Yeah, which is basically the plot I was showing you before, but only the noiseless TOD. And here is the pointing out that this is the precession period. We can check that the non-idealities are doing something by simply taking the difference between the non-ideality, the case, the TOD with non-idealities and the TOD in the ideal case. And something is happening, even if it's not super clear what. I mean, it's not really readable, this plot, but yeah. And for the noise, this is how I was running DAC. I am reading all these parameters by the IMO. I've been defining these variables earlier. And then just generate a realization of the noise, which I plotted together with the noiseless part. This is the plot of the power spectrum that I was showing you before. And for the dipole, I am taking, what I'm taking from LiteBIRD sim is this spacecraft file. I modified, but really a minor thing, just for it to be able to run without the LiteBIRD sim framework. And I am importing the spacecraft orbit function and spacecraft position and velocity. The spacecraft orbit function is needed to know, to define the orbit of the satellite, and this position and velocity return, of course, position and velocity for the satellite given the orbit and given the time and how long do I want to observe and which is the frequency that I need this position and velocity. So the code returns the velocity for the spacecraft at any point, at any time that I need to. And then I'm using this that is also borrowed from LiteBIRD sim, this function that computes the dipole given theta phi, so the direction that I'm looking at, the pointings that I'm looking at, the velocity, temperature of the CMB, and a few other arguments. And I just fill this dipole TOD array with all the signal and I get to this. So there are a few improvements that I would like to discuss with you that I would like to take, but before doing that, I just wanted to show.
By the way, where do you get the velocity? Which velocity is this? Is this also given by the satellite orbit routine, or?
Yes, I'll show you.
So it's
I get this velocity I get from this post-vel. Okay, I get from this spacecraft post-vel function that was, is in the dipole module of LiteBIRD sim. I'm importing it from the spacecraft file. So
this is time dependent then?
Yes.
Okay. If you go down, so you have this vel test, then you have v_kilometers per second. So how did you go from one to the other? Are they the same things?
But wait, then just a second.
You just go up a little bit. You have the compute dipole for one chunk total from ring T. Where does it come from?
Yeah, but this is just the name of the argument.
Okay,
right?
that's the name of the argument. Okay.
Because it's the definition of the function, and then I give them. I define vel chunk from vel test, which is the velocities of the associated to the observation in one chunk for beamconv, and then I feed.
Okay, good. So these are all time independent. Okay.
Yeah, and for each time, for each time you have a three-dimensional vectors that tells you like the vector of the velocity.
Yeah, and does this velocity include solar motion also? Because it looks pretty big. I wonder if that velocity includes everything or just motion of the satellite. You know, what the velocity is with respect to, I wonder.
Yeah, I was talking to Maurizio and he said that it should include everything, but
Okay.
I would like to be sure and to test it, like to think a bit more about it. But
Okay.
he was saying that it should have everything. Okay, so
if that's about 300 kilometers per second, then yeah, it should include everything. So probably you get some term that's constant, then some small modulation on top of it. So you can just plot velocity, so delta test as a function of time. And if that just gives you some small fluctuations on top of 370 kilometers per second, then you know it's everything.
Okay. Okay, then yeah, I will definitely do that. Thank you. Yeah, so before going a little bit through the modifications that we would like to do and the improvement that we would like to do, I just want to show you something that we see in the ideal case that shows that everything is working fine, at least for the halfway plate implementation. If you write down a data model with the diagonal halfway plate, you get that the signal that you measure depends by, of course, the Stokes parameters of the sky signal and the Mueller matrix elements of the halfway plate. And these C and S quantities are sine and cosine of some combination of the angles that you see in here. And if you take the difference between the signal with ideal halfway plate and the signal without halfway plate at all, you get this function, this expression, where the interesting thing is that psi is the angle of the direction sensitive to the polarization of the detector with respect to the focal plane reference frame. And when you have two, it's not, okay, when you have two detectors that are orthogonal one to each other, then this sign gets a minus sign. And this is something that we could see in the simulation by working only with the ideal halfway plate and comparing it with a case without halfway plate at all. So I don't know, I think this gives some confirmation that everything it's going okay. And then, yeah, the main things that I would like to work on to make this more realistic are including the frequency dependence in order to really account for halfway plate non-idealities, not only giving a single frequency. The most trivial thing to do, which I will probably try, would be to run the simulation for a bunch of different frequencies and then integrate on the frequency afterwards. Use some more realistic beam shapes because so far I'm only dealing with Gaussian symmetric beams, and then adapt the pipeline for production purposes. But I think this is something that I need to do even just to get to these two stages, because probably it would get a bit more expensive and I need to run it on a cluster rather than on a simple Jupyter notebook. And once these things are implemented and we check that everything is fine, we had a few ideas about how we could use this pipeline to more scientific purposes. And one thing could be to study how the non-idealities of the halfway plate affect the measurement that we can do of the birefringent angle beta. And in particular, it would be interesting to figure out which requirements we have to put on the non-idealities of the halfway plate in order for the systematics on beta to be small enough to be manageable. And then, for instance, we could again use the study how the non-idealities affect the EB angle calibration and how the non-idealities affect the QU maps of tau A. So I think working with beamconv and being able to really account for the halfway plate non-idealities is going to be really necessary if we want to make some prediction for an experiment that is so precise and with so high requirement as LiteBIRD. And that's it. I think I'm super early. I hope you have questions.
Yeah, thank you. You are on time. So any questions or comments for Marta? Let's see. So can you go back to this bubble diagram that you showed at the very early stage?
Yeah.
So yeah, I just wanted to point out that the scope of this CMB-INFLATE, right, it really fits in nicely here because this top, both of these boxes basically are work package 1. So you have halfway plate specifics and noise. Okay, they are working on creating realistic noise model, including cosmic rays and electronics. So this goes into the duck box. Then they're also working on halfway plate and optics. So that goes to the top left box. So these are all WP1 thing. And then basically you're going to take, so you have everything ready basically. And then you, in the end, you know, after, you know, how many months that we wrote in the proposal, I forgot. You will be basically taking them and integrate them into the pipeline and done. Right? Then you get TOD. And what's missing in this diagram yet is you then have inputs, then you have output, right? So there's a bubble that goes out from the TOD bubble. And this will be work package 2. That will be doing the map making. Then work package 3, which will be doing component separation. That's right, yeah. So this all fits very nicely. So I thought, you know, I just wanted to comment because that's exactly the scope of this project. I have some programmatic question actually. Maybe someone can comment. So purpose of this CMB-INFLATE work package 4 is to have something available to the whole community. Now, Malta's stuff is based upon public codes. That's good. But one thing that's not quite public is IMO. And I wonder what to do with it. I mean, do we just force people in the community to use the same format as IMO or wonder, right? So I don't have a good idea.
We can do something similar to what we did for, you know, the 2 beamconv papers that we published so far, which was to make a fiducial satellite with you know, fake, you know, optics are realistic, but they're not the same optics that are used for LiteBIRD. And we don't actually have to use exactly the half-wave plate Munimatrix that is described in Giampaolo's results. We can use
that's right. So actually, sorry, I wasn't really worried too much.
You're talking about the interface, aren't you? You're not talking about
actual numbers. That's right.
Okay.
So we could kind of make the default the format of IMO and then include that in the package for distribution. Or not? I mean, that's the choice we have to make.
It's an interesting question, given that it's not clear that IMO's structure is necessarily stable at the moment anyway.
Yeah, that's right. Yeah.
So I don't know. I mean, this is.
At the moment, I think pipeline is modular enough that I could take any kind of specification. But maybe this is a question for the community, right? What kind of standardized format we should use for instrument specification like this? I think that's an interesting question.
I'm not sure it helps, but in the LiteBIRD simulation team, there is some kind of substitute IMO until we worked on that before we had the access to the official one over the net, and that's some sort of XML format. Maybe we should talk to Maurizio about this. I think this can be used as well for substituting the official interface fairly easily. That was the original plan anyway.
Yeah, thanks. Yeah, because this really goes in the direction of, for example, ground-based community is trying to come up with this unified scheme, unified format, and so on, right? So that could well be one of the things that we could create as well. Ted, you can speak.
Sure. Yeah, it's just late here. Yeah. So our nominal placeholder is just a small class that we dump and load to HDF5, but individual specialized experiments can, load instrument information from wherever. So for example, for LiteBIRD, we could, we would implement some class that would read the IMO for a particular observation and construct the focal plane properties in memory, directly. So, but that's just the format that we use for, for these, sort of general simulations that aren't tied to a particular instrument.
Yeah. Thanks. Yeah, that's useful.
I mean, I guess that's the critical point, though. If this is getting pushed into the public domain, we can't afford to tie it to a specific instrument or whatever.
Right. That's right. Yeah.
And also there is, I guess it's a small issue, but everybody in the CMB-INFLATE consortium, in principle, should be able to, to work on this and use data. And so if stuff is internal to LiteBIRD, there might be some issues there. But
yeah, that's right. So we can just randomize the numbers in IMO.
But so actually, most of people are within LiteBIRD, right? So it might not be a problem for us, but we have to check.
No, but that would be a good stress test, right, over the pipeline. Just assuming that some of the members don't have access to LiteBIRD proprietary information, then we have to do something, right? So I guess it's always good to start thinking earlier, I guess, so that we can make the pipeline more flexible and portable.
Yeah.
Yeah.
In terms of actual values, I mean, there are publications with values in, so if those are used,
that's also true.
That's fine. That's fine.
That's true. Yeah, I think that's useful because, if you, for example, if people wanted to do something for Pico, they just look at entry that's required for pipeline and they are forced to fill them in. But this is important because they can't just ignore many of the complications and just run it, right? So having something that's required as an input, I think it's very helpful anyway.
I think we should ask, formally LiteBIRD to provide an IMO, which can be used for this program. I don't see any issue with that.
It's okay. Yeah,
that makes sense.
Well, they'll just say use the values that are in the public domain, and then you're back to exactly what the interface is, and not necessarily tying it to the specific LiteBIRD one.
No, but I think they should see the value in just putting the values from the public domain into some small publicly accessible IMO in the same format that the full one is.
Yeah, I think LiteBIRD can do a great service to the community by making the version that's for public, right? So we have version control of IMO, but maybe you could have like a public version of IMO as a subset.
Right.
Yeah, that would be, I think, super useful.
Well, that's a request to the IMO team. Then I suggest that someone makes that.
Guillaume, are you?
Okay, I do that.
Yeah, good.
I expect this will be supported by many other LiteBIRD members as well. So I think this is not wasted effort.
Oh, not at all, totally right. Yeah. Thank you very much. Good, then Marta, thank you.